So I think Shalini will be presenting the screen and will be beginning the session now.
Yes.
Yep.
Hi all. A warm welcome everyone to the introduction part of quantum computing. I'm Shalini D. I am a systems engineer working in Infosys for a couple of months. And also I'm a former QWinten 2022. I participated in the QWinten part. And now I'm an intern in Qubit by Qubit. I also got full scholarship in that. And this is about me. Before starting, am I audible for everyone? Is my screen visible for everyone?
Yes, ma'am, we can hear you.
Yeah. Okay. And okay, before starting now, we can. I wanted to say that this is a pure discussion session. It's not about I am teaching or you're listening or some not like that. We all in the same place. We all come to learn something new. So whatever I know, I am teaching you with all my efforts. Whatever you know, you also can say me. I'll be so humble and accepting all the things from you. We all are here to learn, okay? And whatever questions you have, you can ask me. I will try to answer to most of the things. If I don't know something, I will learn and come to you, and we can discuss about that also. Is it okay? And this, I want this conversation to be two-way. Is it okay? I hope everyone agrees with that.
Yes.
Okay. Thank you for the reply. Okay. Um, we all here to know about quantum. So the first question is obviously, what is quantum? What do you know about quantum? Is anyone here to say what is? You can just explain, like what? Not even explanation. Just say one or two words. What do you know about quantum? That is enough. Be it wrong or right, don't think. We are just here to learn. Okay. Keep this in mind. No worries at all. Okay. You can break the ice. Anyone can break the ice and start. Please don't see the PPT and answer. Just say whatever you know about quantum. I hope everyone is a beginner or someone knows about something about quantum. Hello, am I audible?
Yes,
I
ma'am,
think
you are audible.
Okay.
some of us know a little bit. We just
Okay.
started learning. Most of us, we've attended one or two workshops.
Okay, ma'am. No problem. So I will start. No problem. No worries at all. So quantum means like how much. In Latin terms, it means how much. This word, how much, or we can say about quantity also. Why and how this word came? How much this word? How much came from the Planck's constant? Okay. Now we are going to discuss about the basics of physics, fundamentals of physics, like Planck's constants, uncertainty principle, and the experiments made. Okay, and quantum theory is
Hello.
completely hello.
Hello, Shalini. Sorry to interrupt. Can you
Yes.
please use the slideshow mode and start
Okay.
the presentation from the beginning so that will be full screen
Okay.
and everyone will be able to. Yeah,
Okay.
exactly. Yeah. So now you can use the arrow buttons.
Yes.
Yeah,
Thank you,
yeah,
sir.
yeah.
Thank you.
Okay.
Okay. So yeah. So quantum means like how much, as I already mentioned, how much. This word how much is derived from the Planck's constant. We are going to see how Planck's have derived quantum. He is the pioneer of quantum computing. Earlier now, in 17th and 18th century, Newton was a main hero in physics. Okay, he said about displacement. We all, there was some other scientists also, Galileo, and some more people who have discussed about displacement, velocity, acceleration. All these are, we can see this in the real life also. For example, if you have a box and if you displace that, if you use force and push that box will be displaced to some other part. So these kind of real life situations are discussed in 17th and 18th century, and those people and those scientists that time haven't touched haven't touched the subatomic particles. Okay, now but in the later 19th and 20th century, they slowly started to get into the quantum field, I mean to the subatomic particles, just because of the discovery of Planck's constant and uncertainty principle. And what we are going to discuss what why Planck is so important in quantum right now. Before we discuss about Planck, we need to know about the basis of the electromagnetic spectrum. I hope we all have studied about electromagnetic spectrum. Is it? Am I am I right? We all studied in class 11th on 10th and 12th standard. Also, we have got some 2 mark, 3 mark questions also in that, right? Okay. Now, it's a quick question to everyone out there. Like, what is light? What is made of light? Light is made of what? Can you say? Can someone say what light is made of, or just give some what you know about light? We need to know about that now. We will discuss about it. Can some?
Photons.
Yeah, you're right. Light is nothing but photons. That is first point. You have said it very correctly. That word photon is very important. So light is nothing but photons. Also, the second most important property is light is in the original form is in the superposition state of both wave as well as particle nature. Here I'm saying original means when it is not disturbed by any matter. What is matter? Matter means which has mass. The metals which we use and all these things now they have mass. Electron also have mass. So light is one which doesn't have any mass. It is zero mass. We all have studied this, but we can recall in this session. This today we are going to recall whatever we studied in physics. This is very important. Okay. So the if someone say about light, two things should come in your mind. First is light is nothing but photons. Second, in the original state, light is in the superposition state of both wave and particle. Okay, only when it depends upon the experiments. It depends upon which matter it tries to communicate in the sense that when the light collides to the metal, it becomes photons. It when it collides with the in double slit experiment, when it collides with a slit, when it passes through the slit, it behaves as wave. So it depends upon the matter. We will discuss about this. Okay. In the middle you can see this is the visible light spectrum. To the right side we have the wavelength. Okay. So in this electromagnetic spectrum we have two sides, left side and right side, and between we can see the visible light. To the left hand side we have frequencies. We have frequency. If you have high frequency means you have high energy. To the right hand side of the spectrum you have wavelength. Wavelength means you have very less energy and very less frequency. You can consider like this also. Frequency is directly proportional to energy, but frequency is indirectly proportional to the wavelength. That is the reason why we are using microwaves in our house. Why can't we use gamma rays or x-rays in our house? Can anyone answer? Because I've already answered this indirectly. Why can't we use gamma rays or x-rays in our house? Why do we use only microwaves? Why? Can anyone answer for this?
They require too much energy to produce.
Yeah, you're right. Energy is an hero here. Okay. Gamma rays and X-rays. See, you might also remember in X-rays, when we take X-rays of X-ray, they don't even allow another people to enter into the X-ray hall because the frequency is so high. The radiation is high. Why the radiation is high? Because the energy is so much. Okay, it can go inside our bloodstreams and cause some catastrophic effects also. So why we don't use x-rays and gamma rays in our house? Because the energy is too high, that radiation is so powerful. And why we use microwaves in our house? Because it has very less frequency and very less energy, but you have larger wavelength. So why we are using microwave oven in the house? This is the basic and difference between a wavelength and the frequency. Wavelength and frequency are inversely proportional. When the frequency is higher, the wavelength is shorter. When the wavelength is higher, the frequency is shorter. That is so why in the above we can see you have increasing energy, and below you have increasing wavelength. They both are going the opposite direction because of this reason only. And in between we have visible light spectrum. Okay, I hope you have recalled what light is and what electromagnetic spectrum is. I will go to the next part. Now, here comes the hero of quantum. Why I'm saying hero? You will come to know this very soon, because earlier, now, earlier before Planck, people were thinking that light is just a wave. Light only as wave nature, and also they don't have an answer why light. I already mentioned that light has zero mass. Okay, how can these people didn't understood how come the light with zero mass interacts with the matter which has mass. They don't have an answer for this. This is and this is answered by Planck constant. This is answered by Planck. Okay, what he did, he did black body radiation experiment. What is black body radiation experiment? It is a spectrum of light emitted by an heated body. When you for example, um, in a real life example I can give you, you are taking a vessel and then you're keeping, for example, you're taking aluminum vessel, okay, and then you're keeping it on the gas stove. If you forget for 1 minute also, there it gets heated up so fastly, and there is some violet color light comes. You can also check it when you try to use it in the real life. So it is like a spectrum of light is emitted by an heated body. In this experiment, he conducted in this experiment conductor, he came to a conclusion that light is nothing but it's a discrete package. It comes in different in set of packets. You can ask me why light is like in the discrete package, light is not continuous. Because of the frequency. If you keep changing the frequency now, the energy is also changing. Okay, this is the reason why energy is directly proportional to the frequency. When you keep changing the frequency, the energy is also changing. So it comes in a it comes in package. It is not continuous in nature. That is that is found out by Planck only. So that discrete set of packets is called as photons. It comes in packets that we call that packet as photons. Okay, why it is not continuous? It's because the frequency is changing. When we change the frequency, the energy is also changed. And so why he has given a very nice postulation, very nice formula as energy equal to h into frequency. H is a Planck's constant and V is a frequency and E is energy. And E is the reason why scientists have went deep inside the subatomic particle. Okay, subatomic particle is nothing but proton, electron, and neutron. We all know this. And with Planck's constant only, many people have many scientists have found out. For example, Bohr, Bohr model. The modern Bohr model was found by, was derived from Planck only. And uncertainty principle. Weinsberg also used Planck's postulates only, as well as Louis de Broglie has given a very nice explanation about the photoelectric effect. All these scientists have took inspiration from Planck constant. So why I'm stressing importance to Planck? This is the reason. And next we are going to. I hope everyone is clear till now why I'm stressing upon the basic fundamentals. Is there any doubt?
It's clear.
Hello?
Yeah, it's clear.
Yeah, clear. Okay. Thank you for reply. Now we are going to uncertainty principle. Why we are going to uncertainty principle? Because when you know about, because I already mentioned that light has dual nature, wave nature as well as particle nature. Depending upon the matter it collides, it becomes either as a wave or as a particle. Okay, so here we need to know, here in uncertainty principle, Weinsberg has stated that if you know the position and you can't know the position and the momentum at the same time, because I will say why. In classical physics, if you in classical physics, this postulate doesn't apply for the classical physics. This uncertainty principle, like knowing the position and the momentum at the same time, is not possible. Is not applicable in the classical physics, because in the classical physics, if you know the speed, for example, you consider a car. Okay, if the car is going at a particular speed, okay, you know the destination, you know the kilometer what you want to achieve. Okay, if you are going in the particular amount of speed, you can calculate the time you can reach by speed equal to distance into time. It is very easy. That this principle is not applicable in classical physics because of this reason only. But uncertainty principle is made exclusively for for quantum physics, because light as a wave nature. Now you consider light as a wave nature, wave as peaks and troughs. Just when I try to say wave nature and particle nature, now just try to visualize wave if I say wave, then just consider it as a wave. It has peaks and troughs. When it has peaks and troughs, can you know um, can you know the desired position of the wave? Can you know where the wave is located particularly? Because it is keep on moving. It has peak, it has trough, it has positive and negative. Peaks and trough, it has up and down. You can't have the particular position of the wave. So why? Even if you try to measure the position of a wave, you will tend to lose the momentum. You will lose. You can't measure the speed and position at the same time because of this uncertainty principle. Okay, if this is to the wave side. When I consider light as a particle, when I say light as a particle, just imagine particle as a marble ball. I mean, or a rubber ball, a small rubber ball kind of thing. Okay, it has a position, right? You can place that. Okay, you can fix the desired position in a graph, or something. Okay, you can able to fix a position for that particle. But when you try to know the speed, you can't manage both. You can either measure the position, particular defined position, or you can only measure the momentum. You can't do both at the same time. This is the basic principle of uncertainty. This was given by Weinberg. And why we are studying Planck's and uncertainty principle is because in quantum computing, electron is the main hero. Okay, we are going to study electron. If I say qubit, then we are mentioning about the electron only. All these things in subatomic particle, we study about electrons mostly. We study about electrons only, and that electron is used in qubit. That one qubit which I'm going to say in quantum computing is one electron. So why we are brushing up the concepts, basic concepts. That is the reason why I'm going to coming from the very basic physics. Okay. And uncertainty principle, as he has given an equation, del x into del p is greater than or equal to h divided by 4 pi. We don't have to go in depth of the equation and all. We just have to know it. Okay, h is a reduced Planck constant, and del x is uncertainty in position. If you try to find the position, you can't be accurate with momentum. If you want to find momentum, you can't be accurate with the position. That is the main concept behind this uncertainty principle, and this same concept applies in the quantum computing also. So why this concept is important? As I already mentioned, Planck's constant is the basic for as at any scientist have took inspiration from Planck only, about the photoelectric effect, Bohr atomic model, de Broglie wavelength. All these found inspiration from Planck. Yes. Now we came to the most important experiment of this century, double slit experiment. Okay. Why I'm saying important is, I already mentioned light behaves as a wave as well as a particle. In original position, it is in the superposition state of wave and a particle. In this double slit experiment, we are going to prove that light behaves as a wave. Okay, and photoelectric effect, we will say how how light behaves as a particle. So why both experiments are very important. Okay, why we are saying double slit? Why it can't be single slit? Can anyone answer for this? Hello? Am I audible to everyone?
Yeah, we can hear you.
Okay. I think okay, I will save myself, no problem at all. Okay. Why we are considering double slit and not single slit is, if you use only single slit, the light which travels, it becomes a straight line. You can't get the wave nature of light. That's why we are not going for single slit experiment. That's the reason why we are going for double slit experiment. We need to prove the wave nature of light. So why we are going for double slit experiment? As from the this slide is self-explanatory. When you have the light source, when it passes through the double slit, it has the first slit as a separate wave pattern, and the second slit as separate wave pattern. Okay. In when two waves, when two I mean wave when the wave from the first slit and the wave from the second slit interfere with each other, they can be either constructive interference or destructive interference. Constructive interference means when the amplitude matches, when the amplitude of the wave matches. What is amplitude? We all know wave as troughs, peaks and troughs. When those amplitude matches, it becomes constructive interference. And if the wave doesn't matches, if the amplitude doesn't match, it means the peak and the trough of the wave doesn't match from the two slits. It becomes destructive interference. Okay, so it can be a constructive interference also, it can be destructive interference also. So when it goes so at the end you have that black box kind of thing, like a black rectangular kind of thing. So in that you will have dark fringe or bright fringe. Bright fringe represents it is constructive interference, dark fringe represents it is destructive interference. So we can prove that light is in the wave nature until until when the measurements are done. We pass the light source through both of the slits and we can prove that light is a wave. But when we start measuring it, it becomes as a particle. You can ask why it is behaving, why in this particular experiment light is behaving as a wave, why it is not a particle. It's because this is nature. Physics is nature. We don't have an answer for everything in physics. That is the beauty of nature, right? For this experiment it is supposed to behave as a wave. For photoelectric effect it is supposed to behave as a particle. This is how nature is. Sometimes we have to I have these questions like you, why for this particular experiment it is behaving as a wave. I too had the same question, but when I dig deeper into the basic things, I understood that for some things we need to accept. We can't search answer for everything. That is how nature is made. So physics is of course nature. We can't see from the eyes. We have to just accept and realize it and go on. So I hope a double slit experiment is clear. It depicts about the wave nature of light. Now we are moving to another era in defining whether a light is a particle or wave. Earlier in double slit experiment, we have proved light acts as a wave. In photoelectric effect, we are going to discuss light acts as a particle. Particle means you can just imagine like a small lump kind of thing, okay, like a small ball. For the visualization, because these things we can't see in our eyes, we have to go to the lab. We have to have the access to the lab to do experiments and get measurements for that. We can't do that, but we just have to visualize things. That is how it is. Okay, so you have a metal surface. That metal surface we can consider it as an alkali metal. Okay, this alkali metal, in that alkali metal, you're passing an ultraviolet light. Okay, when the ultraviolet light is passed, why I'm mentioning about the ultraviolet rays? Because it has high frequency now. Ultraviolet rays, it has more frequency. When you have frequency, when you have more frequency, it behaves as a photon. It behaves as a particle. Okay, when you have see photons is everywhere. The beauty is photons is everywhere. Okay, depending upon the frequency only, it behaves as a particle or behaves as a wave. When here the frequency is I am using ultraviolet light. When we discussed in the electromagnetic spectrum, I have mentioned that left side of the spectrum is completely to the radiation side and the right side is completely to the wavelength side. We can't say gamma waves, we can't say micro rays because of the frequency. Micro waves and gamma rays. Rays means radiation. Radiation means frequency. Waves as very less frequency and very less energy also. This is what I understood from the electromagnetic spectrum. I got this in intuition, you can say. Like when you dig deeper in physics, you try to understand more and more visualization side also. Okay, now we can come to the photoelectric effect. So this incident light is ultraviolet rays and this metal surface is alkali. when you incident the ultraviolet rays, what will happen? The electrons take the energy, from the photons, and then it emits and then the metal surface have electrons because metal has mass, right? So when the light is incident, ultraviolet rays are incident to the metal surface, the electrons are emitted, okay, by getting the energy from the photons. And photons lose energy, electrons gain energy. So electrons are escaped, and some amount of the energy is going to the kinetic energy. Okay, so this experiment shows the particle nature of light. I've already discussed this: increasing the frequency of light, increasing the energy. So in photoelectric effect, electron absorbs the energy from photons and become excited and released. We have discussed, and this the previous uh, picture is self-explanatory itself. So this photoelectric effect is mainly done by Einstein. So Einstein is also took inspiration from Planck. Okay, so Planck and Einstein relation. So he has also given the same equation: E equal to hf. F means frequency, h means Planck's constant, and E is energy. So I hope I'm clear. I hope we are all clear why we are studying this and with all the experiments done. Double slit is to know the wave nature of light, and photoelectric effect is to know the particle nature of light. So, de Broglie, we have to pronounce him as Louis de Broglie. Okay, um, in the particle nature of light, we have seen the electrons are emitted by gaining the energy from the photons. Louis de Broglie was thinking what happened to the emitted electrons. That emitted electrons, see, the electrons are emitted in this photoelectric effect, right? Other scientists were only thinking, only debating about the particle and wave nature of the light. But Louis de Broglie is the one who thought and what happened to the emitted electrons. His main experiment deals with the emitted electrons only. Okay, when a photon with high frequency hits the metal surface, electron absorbs energy and escape. So Louis de Broglie's question is what happened to the escaped electron which absorbed energy from the photons. This emitted electron is, again, they send that they captured that emitted electron, and they send that emitted electrons in the double slit experiment. This is done by Davidson and Germer. Okay, they both, these two scientists have got that emitted electrons, and they send that again in the double slit experiment. They came to know that emitted electrons behave as a wave-like frequency. Wave-like nature. So de Broglie came to a conclusion that electrons exhibit wave-like properties. Light also has wave and particle nature, but light has zero mass, na? But here electrons having mass behaves as a wave. He found this postulation, and this came out to be true by using the double slit experiment. And he has given a famous equation: lambda equal to h divided by p. We can just understand lambda equal to h divided by p. We don't have to go in depth about the equations and all. We just have to go in a flow why this is happening. So electrons also have wave-like properties. This is proved by Louis de Broglie. This is the reason why we are going to Louis de Broglie. Okay. So till now, is everyone clear, or anyone has any doubts?
It's clear.
Clear. Okay. Okay. Thank you so much. Okay. Now we are coming to the most important part: classical versus quantum computing. Let us skip this slide. I will explain this slide after some time, because it will be a flow. When you try to understand all the other parts, no, this flow will be self-explanatory in nature. So why? Classical bits. We all know, we all studied bits. Bits means 0 and 1. It is binary in nature. We all know that also. Okay. It's like but in the real sense, inside the computer now, it is pulses of electricity. When it is on, it is switch on. When it is off, it is off. So why it is binary nature, either or. Okay. So we all are very much aware about the classical bits. Now, bits. Bits are zeros and ones. Now we have gates and or not. We all have studied about this also. So what is the relationship between bits and gates? Bits as zeros and ones is utilized by gates. Gate manipulates the bits according. For example, AND gate. If you give 0 1 1, we get 0. If you give OR gate, we get as 1. 0 and 1. If you give 2 bits, we get 1. For in AND gate, we get 0. Right? It is for example, for in the NOT gate, if you give 0, you give 1, you get 1 as an output. If you give 1, you get, it is complementary. Okay, so gate utilizes the bit. You can, the more appropriate word is, it manipulates them according to the need. That is how bits and gates are related. Bits is used by gates. Gates manipulate the bit according to the user needs. Okay, next is circuits. If you, we in this part we have explained about the gates, which is only one, we have only explained in a separate way. But in circuits mean, circuit means you have a combination, like hundreds and millions of these gates form a circuit. Okay, this is the basic model of circuit. In this we have hundreds and millions of gates. For I have read somewhere like you have 45 millions of gates. That gate all combine to form a circuit. That is what a relationship between classical bit. Classical bit is utilized by gate, and gates manipulates bits, and thousands and hundreds and millions of gates form classical circuit. So this is like a flow. Okay, now we have algorithms. So now we have formed a circuit which has thousands of gates, and that gate uses bits, which is 0 and 1. Now we are going to the algorithm part. Classical algorithm like linear search, binary search, sorting, and trees, they all belong to the classical algorithm. So these algorithms, now we will use it in the circuits for the running purpose, like for the running purpose, right? We all know what is algorithms. It's a step-by-step instructions executed by the combination of hundreds and millions of gate together. That is called as circuits. So algorithms, we we dump that algorithm inside the circuit to run it. Okay, for depending upon the applications. And here comes the last about applications. After getting a bit, after forming, after using that bit in the gate, and after constructing the circuit, we are dumping the algorithms there, and then we are modifying it according to the application. For example, if you need a game, for example, you need to use laptop, you have a separate set of algorithm for that. For web browsers, it is different. For streaming services like Netflix and Amazon, it is different. So it is depending upon the purposes only. So and this is the relationship between bits, gates, classical circuits, algorithms, and application. So this is how a flow should be. We start from small part and we go to the application part. I hope I am clear with the flow. How bits is related to gates, and gates are related to circuits, and how algorithms are used in the circuit, and how they are uh, used in for a specific purposes. We have seen the applications also. I hope this is clear, because I have taken it very precise, because we all know it. We are technical. We are belong to technical side, so I didn't went too deep into the classical side. Is it okay? Is everyone clear with the concept, like classical computing,
Yes,
Yes.
Okay, okay, ma'am. Now here comes the real part, history of quantum computing. Before going to the quantum, we will stop till the history part, and we can continue quantum computing from tomorrow onwards. We can just go through the history of quantum computing right now. Okay, so the timeline, it started from 1980s itself, even before I was born. When my mother and father was in their early teenage, it started way before that time, 1981. Oh my god, it is so much. We sometimes we see the timeline. I feel proud that we are learning something. In a We are learning something which started way before I was born. This is something quite mind blowing thing. This is what I feel. You can, I don't know whether what you feel, but this is what I feel. I wanted to share this. Okay, coming back to the topic. 1981. Feynman and Benioff. Feynman is a famous physicist. Famous physicist. We will discuss about Feynman tomorrow in quantum computing because he has discussed. He has given a vast contribution to quantum computing, just like Planck. We will discuss about him tomorrow. Feynman and Benioff proposed a simulation of quantum mechanical system, and I've just mentioned 2 points about Feynman. Feynman has given contribution to the electrodynamics, like which is a theory of interaction between light and matter. Light, we have already discussed what is light. Light is zero mass, and matter has mass. So Feynman has discussed about that, and we invented pictorial representation of particle interactions, like Feynman diagrams. If someone has some interest, we can go and search like what is Feynman diagrams. I didn't include this because it is way out of our topic, so I didn't include that. And same again, another scientist in 1981, Yamamoto and Igeta proposed the first forms of quantum bits and quantum gates with atoms and light. And again, in 1986, Feynman introduced the modern notation for quantum gates. So in 1981 they started with the quantum bits, and 1986 they went to the quantum gates. And Dutza and Josa, and these two person are this algorithm is very important. It is in the advanced topic. We will also cover that in the upcoming sessions. But this Dutz and Josa algorithm is very much important in quantum computing. I can say this. Discovered quantum algorithm, which is exponentially faster than classical algorithms. So this happened in 1992. In 1994, first physical quantum gates were built using gold trapped ions. And 1994, Shore is another algorithm which we use like Dutz and Josa. We have Grover also. We will come to that in the later stage. But Shore is an important algorithm again. Worked on algorithm contributing to cybersecurity. And Schumacher coins the term qubit for quantum bit. So it also earlier it was quantum bit. Earlier in the first forms in 1981, when you see they just proposed the first forms of quantum bits. They didn't mention as qubits, but in 1995, Schumacher has coined the term as qubit for quantum bit. In 1998, they first demonstrated the quantum algorithm in 2-bit quantum computer. So 1998, the first demonstration happened in 2 qubit. 2 qubit means here 2 electrons. We have to remember this for the entire session. Okay. In 2017, cloud-based quantum computing. So quantum computing has gone to the cloud level in 2017 after 2 decades. And 2019, first demonstration of a quantum computer outperforming the classical computer was demonstrated in 2019. Today I am going to stop till this part, and tomorrow we will discuss about quantum computing in depth. Today, let it be a recall session. Let it be a normal session. Tomorrow we can start going more and more in depth. Okay. Do you have any doubts till now? Like you wanted to share something, or you wanted me to improve on myself? Is there any point should you need to add? You can speak right now. I will stop sharing the screen. We can have a normal discussion right now. Yes. Does anyone have any doubt till now, or wanted to discuss something? I'm feel free to ask.
So, like, you showed us one kind of a flow chart about how, like, you have bits in the lowest part, and then gates control the bits, and
Yes.
then the circuits control the gates,
Yes.
algorithms control the circuits, and
Yes.
finally the applications control the algorithms.
Yes.
So, can that concept be applied like in every scenario, like even if we take it to like quantum computing as well,
Yeah.
or cloud computing, like in any of these computational scenarios, like most of the cases will these work?
Yeah. Actually, now this basic thing applies in the same quantum computing also. The concept is same everywhere, but this classical computing doesn't support the subatomic particle. In quantum computing, we use electrons. So why I mentioned, in classical bits we call bits. Bits is not applicable in quantum computing. We in quantum computing we say qubits. Qubits means one qubit means one electron. We deal with the subatomic stage. In classical, we don't deal with any subatomic stage. To answer your question, this basic concept applies even in the quantum also. Even bits work on the gates, and gates, hundreds and millions of gates form circuits, and circuits become, I mean, we dump algorithms in these, and depending about the application. So this concept is same even in quantum computing, but the research is being made to improve the amount of qubits to be used. You will get to know a lot of concepts tomorrow about bits, qubits, and all these things. I'm going to discuss a lot about these things tomorrow. I just wanted to I want to keep this session as simple as possible to recall the basic part. I don't want to dump everything in the single day because it is so difficult. Because I also came from the beginner side. I know how much it is to take everything at one go. So why I didn't discuss about this. Okay. Wait, I will share the screen. I stopped sharing the screen. Huh? I will share the screen and show it to you. I forgot that I stopped sharing it. Yeah, sorry. Okay. So to answer your question, the same concept applies even in quantum also. But the basic differences in classical we use in classical we use only bits. Here qubits. Qubit means electrons. So why all these physics concept was come into picture in quantum computing. So this is the this resembles with classical, but only thing is here it is quantum. Quantum bits are applied to the gates. Gates manipulate the bits, and thousands, hundreds, and millions of gates form circuits and algorithms. We dump into the algorithm. We dump the algorithm in the circuits to run according depending upon the particular application. And quantum is morely specifically related to the it's application oriented. Okay, that's the main drawback of quantum. We will tomorrow we will discuss about this. If I start saying, like, I will start speaking a lot about that. So to answer your question, this slide answer your question. I hope I am clear.
Yes, ma'am.
Okay, thank you. Yes. Any other doubt? You all have got a some clear picture now, like what is it, what I'm discussing. You all got a clear picture, like why I'm went to the physics side, because quantum is not about like a classical part. It is completely into the subatomic world. We discuss about electrons. If I say qubit, it is we are mentioning about the electrons. It is very important to mention, to brush up these physics concepts, because at the later stage we will again go back to the basics. So why I wanted to discuss basics in the first. I don't want to go back to the basics when we come to the intermediate stage. This is the reason, and this is completely a recall session for everyone here. Okay. If you don't have any doubts as of now, can we end the session?
No doubts.
Hello. Yes, Aditya.
I just said no doubts.
No doubts. Okay. Okay. So thank you, everyone. Thank you for your patience for this 1 hour. Whatever you can just go and see the basics of whatever I taught, and if there is any doubt, we can discuss it tomorrow. Okay. Okay. So thank you. I'm going to end the session right now. Okay. We will meet tomorrow morning at 10 a.m. Okay.
Thank you.
Okay. Thank you. Thank you, ma'am. Thank you, friends. Thank you.
Thank you, ma'am.
Yeah.